Welcome, Math 20-3. This is the lesson on 3.4, volume and capacity of spheres, cones, pyramids. The correlating assignment is in your workbook on page 183. Build your skills section. I just want you to do 1, all of 2, 3A and B, 5, 6 ABD, 7AC, and 9. Now, we're going to look at a few different case scenarios because we're looking at how we're going to calculate the volume and convert that in capacity of the following three shapes, which will also have some composite figures. And now let's go to some fancy ones that have already created some real-life case scenarios that have no numbers. Bam! Look at that. Beautiful thing. So, in context, here we go. Here's a lovely little pyramid that someone has built. And we want to know how much space is inside, and so hence we want to know the volume of this. Yeah, it's still on the screen. Good. Okay, so in order to calculate the volume or the space inside, we're going to need to take the, again, length, the width, and the height like a prism. However, in the end, that's all you really have to do. But then, because of this pyramid, this funny shape, in the fact that everything converges to an apex that's not a prism, so we have to take 1/3 of it, or take our volume of the prism, and divide by 3. Okay? So for this question here, I'm going to make a couple estimations, because that's the best thing we can do with a real-life case scenario. If we actually get a tape measure, we could do that just as easily. Okay? So I'm going to assume that these panels that typically would be from here to here are 2 feet, here to here, 2 feet, and here to here, 2 feet, which makes that dimension 6 feet. Hope we can see that. All right. I'm going to make an assumption that this is square, okay, and I'll call that 6 feet. So far on my pyramid, let me just draw one out with my lines here. Lovely. Let's grab another one here. Okay. So far on my pyramid, we've got 6 feet. Whoops, wrong tool. Guess I should go back to the mouse. 6 feet. 6 feet. Okay. But now we need the vertical height inside. All right. Now I can't see that. Neither can you. So we need the vertical height, which is this part right here, because that's going to be the height of the pyramid, or the prism, as well as the height of the pyramid. That would be inside. Not the easiest thing to acquire. So what I could do is I could take a tape measure. In fact, I think I've got some sort of fancy tool here. Let me just take a quick peek. I thought I had an application that's a tape measure. Look at that, a ruler. Let's bring the ruler here. All right. So let's pretend that we can just sort of measure this. Like, we could take a tape measure. That would be practical. We could measure the outside. This is just a ruler. But if we took a tape measure, we could probably get a rough line from the middle of here to the top peak, and we would get the slant height. Let me just get rid of this ruler now, okay? However, because we don't actually physically have one for this picture, I'm going to make an estimation, all right? This guy looks to be maybe 6 feet tall. So we're going to make a nice, beautiful little estimate that the slant height is 8 feet high. Okay? Slant height, 8 feet. Now, here's the problem. We need the vertical height. We'd have our volume if we have the length, which is 6, the width, 6, but we don't have the height. We have the slant height, though. We can consider we can get it, though. Let me just draw you out what we have if we take a cross-section. In red. All right, we've said that this is 8 feet here. Okay. We've said that this bottom part all the way across is 6. So this must be logically 3 feet. And now we need to figure out this one. Okay, so what we're going to do is we're going to use the old right triangle. We have two sides, And we're going to need to use Pythagorean theorem, that a squared plus b squared equals c squared. Which one's which? That's a very valid question. We need to ask which side is which. And let's visualize the Pythagorean theorem again, that we've got the following case scenario. Let's draw it down here. Okay, let's just keep drawing things here. Yeah. All right, there's a square. There's a square. Whoa. Let it go first. And then here's a square. Remember, it's calculating and considering the areas, okay? So this area plus this area equals this one. Now we can figure out this one because we have that dimension. We have the 8 by 8. We can figure out this one because we have 3 by 3. But we don't know this area, okay? Remember that these two red ones add up to the green one. So let's see what we need to do. We'll find the larger one by taking 8 by 8. So 8 times 8 is 64. Down here, that's 3 by 3, which is 9. So something plus 9 is 64, which is the large area. Okay, so to figure out something plus 9 is 64. That means that the area of that left square must be equal to 55. Okay, this whole space here is 55. But we only want the one dimension of that, namely the side. So to figure out the height, which is what we're looking for, we need to square root 55 and round to about 1 decimal place sufficiently. This is a good time to bring the calculator up. Alright, so turn it on. Okay, square root 55 suggests that the height of this pyramid inside here is about 7.4 feet, which looks good because it should be a little bit less than 8 and not substantially smaller, that someone's going to hit their head in there. Okay, so now we kind of say that that's reasonable, and I'm just going to round, okay, to about 7.4 approximately feet. Now we have got all the information we need. We have the height, check. We have the width, check. We have the length right over here, check, and we can divide that by 3. So now I'm just going to move my screen over a little bit, and I can fit more stuff on here. We'll keep calculating the volume of this pyramid, of this tent. So volume is equal to length times width times height divided by 3. Our length of this thing is 6. Our width was 6. And now we just figured out the height of 7.4. So I'm going to use those numbers on the calculator. Clear this off. I should probably even keep on the screen. 6 times 6 times 7.4. So it's 266 would be a prism if this thing was open all the way to the top. Ooh, that's ugly. Anyways. But then I got to divide that by 3 because it's a pyramid and it folds in the middle. So divide that by 3. Where's my calculator? Divide by 3. And our total volume says, whoa, something just weird happened there. The volume of this particular pyramid is 88.8 feet. Now because we had 1, 2, 3 linear dimensions, it's feet times feet times feet, or feet cubed. Ta-da! So this whole thing of this particular pyramid takes 88 feet cubed. All right, let's zoom out and let's move along. I believe I've got some lovely little cones going on here. Oh yeah. Let's move this guy out of here. And one thing we're supposed to consider is cones. And I'm going to use this guy, hand, as a referent. So, similarly to a prism, a cone is kind of like the same idea. We're going to figure out the cone by the idea of it being a cylinder, a right shape, okay, and then it all folds into the middle. So it's really the same as the area of the base times the height, then divide by 3. Because of this folding into the middle, geometrically, we're not going to prove it, it divides out by 3. So if we recall that the area of the base being a circle of the cone, you may not be able to see that, that would be like this space right here. That's cross section. That's going to be a circle. That'd be pi r squared times the height, which is going to be the distance straight down, straight through the middle, which is pretty hard unless you want to get your fingers really messy. You really wouldn't want to measure that, okay? Times the height. And then because it goes and folds up to the middle, this little point down here, because it's upside down, it's going to divide by 3. Okay? Now I'm going to use some estimation skills. My hand, or at least, it's fairly big. My hand, where's my red? All right, here we go, large red. My hand size, about from here to here, is roughly, or even reasonably, somebody's 10 centimeters, okay? And maybe that's halfway more. So I'm going to estimate that the height is equal to 15 centimeters. And roughly, because of interest, let's just make it really easy, 10 centimeters across. That's going to be our diameter, 10 centimeters. Just a rough estimate. Which means the radius should be equal to 5. Okay? And so now we've got all the information. We only needed 2. We needed the height of this cone, straight up and down the middle. Otherwise, we'd have to use that Pythagorean theorem like we did the last question to figure out the vertical height. And now we have the radius estimated, so now we can figure out the volume of this cone, okay, assuming there's nothing on top of there, which there is, filled up completely. Here we go. I'm going to go back to black. So the volume of a cone is defined pi r squared height over 3. So we're going to go pi times radius times height, and then we're just going to divide by 3. So 3.14, we said the radius is going to be 5, and the radius is going to be 5, and the height we said was roughly 15. Here's our linear dimensions, okay? Centimeter, centimeter, centimeter. So in the end, we're still going to maintain a centimeters cubed value. So in sequence, I'm going to go 3.14 times 5 times 5 times 15, and then I'm going to divide it by 3. So I'm going to bring my calculator over here now. All right, clear everything off. I'll just use 3.14 times 5 times 5 times 15, hit enter, divide by 3. So the volume of this cone suggests that it's 300, whoa, that was ugly, 392.5 or 393 centimeters cubed of this cone. But now we want to do capacity. Now capacity means typically in liters, all right? So what's the capacity? Well, we said in a previous lesson that capacity relates the centimeters cubed to liters, or I can even convert centimeters cubed into milliliters. When I've got less than 1,000, which this number is, probably the easiest answer is to use the millimeter. Why? Because 1 centimeter cubed is 1 milliliter. Beauty. So that suggests in capacity, if I've got, let's just round this number off to 393 centimeters cubed, that's equal to a capacity of 393 milliliters. All right. Moving along. Let's just zoom out and find my next question of examples. I believe I've got... Oh, yeah. Let's do one of these ones, because I know that some of my... Whoa! Should actually, like... Some of my students like basketball. Many do not, but that's okay. Some of them do. And we want to know how much air is in a basketball based upon the exterior dimensions of an official regulated size NBA ball. And I've also done it in such a way that because when you look up this data, they only ever give you the circumference, which can be a little bit annoying because we don't need the circumference. So this is actually a two-part process to help you out. All right. So in order to calculate the volume of any spherical type shape, which is basically a ball, the volume is defined as 4 over 3 pi r cubed. Now what this means is going to be way easier to do if we write this out separately. We're going to do this in the reverse sequence. We're going to take pi r cubed times 4, because that's what that top number is, and then divide by 3. We're going to use that procedure. Okay? Now r cubed, because some people may forget, what is that? It's going to be pi times r times r times r 3 times. 1, 2, 3. That's going to give us our cubic dimension, because those are actually one linear dimension used in 3 values. This is the ratio of how it fits, by the way, inside a cube. Anyways, so once we have our pi, or our radius, we just have to multiply itself 3 times, times pi, then times it by 4, then divide by 3. We'll figure out the volume of that sphere. Now we're given the circumference. Because the ball, if you recall, I'm just going to grab my mouse over here now. And where's my shapes? Home, shapes, pictures, shapes. We got a nice, let's add a little gray here. All right, make that a little bit bigger. So what they've given us is the distance around, because that's the way the measurements of basketball and most dimensional things give us. So we have, I'll write it in blue, the circumference of this ball, which is the distance all the way around. Okay, that's 29.5 inches. However, I'm going to use the metric, which is right over here, 75 centimeters. That's the distance around. We don't need that distance around. What we need out of that is the radius. Okay, you might need a recollection that the circumference relates to the radius as taking 2 times pi times the radius. So if you take the radius, times it by pi, times it by 2, you get the circumference. So remember these flow things, folks? If you don't, here we go. If we had r, from that formula, it says we can times it by pi. We can times it by 2, and we're going to get the circumference. Which also suggests it works exactly true the opposite way if we have the circumference. And do exactly the opposite, divide by 2, and then divide by pi, we will get the radius. Okay? That's what we're going to do. I'm going to use my green color here. We're going to take circumference, 75. We're going to divide that by 2. And I'll have to use a calculator for that purpose, which is off my screen. I'll just bring it over here for now. Okay? Clear everything off. 75 divided by 2. Hit enter. Okay, that's 37.5. I've done that. Check. Whoa, ugly. Okay, circumference divided by 2. Check. Then I got to divide that by pi. Divide it by, and I'll use the pi button because it's nicer to use the decimal thing. Okay, and that's it. There's the radius. So the radius is 11.93 centimeters. We'll use a precision of 2 places for now. Okay, because we have to use that over here. Just pull that across now. We have to use that radius for the calculation of the volume here. And I'm going to use that 11.93. I'm going to round it off for our interest's sake. So now, we're going to take pi times r, which is there. Or, I can shortcut that 11.8. Yeah. I can shortcut the times r 3 times simply by cubing it. But I'll do it the old-fashioned way. So pi 3.14 times 11.93 times 11.93. Whoops. 93 times 11.93. Okay. What did I do? Okay. There is the pi times r times r times r. I'm going to times that by 4. Divide by 3. And here's the volume of a basketball. This basketball, way over here now, is 7,108.69. And that, because we had centimeters times centimeters times centimeters from this part right here, gives us centimeters cubed. Now, in the capacity part, very simply, what we can do, remember that 1,000 centimeters cubed is 1 liter. We got 7,108. Let's just round that to 9, just for the interest's sake. Centimeters cubed. We want to know how many liters this thing is. Okay. Well, we got to figure out how to go from 1,000 to 7,109. Well, every time we're going to do this, we're always going from a smaller number to large. We can always take the larger number, which is right here, divided by the smaller number, or right divided by left, so divide by 1,000. And it suggests that, lo and behold, to get from 1,000 to 7,109 is times 7.1. I'll leave that back over here because it should be 2. All right, so times 7.1. That means, in capacity, times 7.1, a basketball has got roughly 7.1 liters of air inside. And you're probably thinking, wow, 7.1 whole liters. Impressive. Who cares about liters inside a ball? Let's find out who would really care about liters inside a ball. Well, I'm pretty sure this guy would be kind of concerned about how much liters of air are inside. Because if there's not enough, he will not have any liters of air with which to breathe. All right, so let's do this. Finding the capacity or the volume of this sphere, because it's really important. And we'll also go and say capacity, because in real life, people really need to know how much capacity and how many minutes, because they could look that up and see how many minutes can you actually live inside of these things safely. This is actually a YouTube video that I found where a guy bought a scuba gear and he bought a canister of compressed air. So figuring he could travel across the ocean, it's probably all just staged, with a canister of compressed air in here to see that he would probably be able to live in there a bit longer, or at least for a few more hours versus a few minutes that they recommend you being in there. Okay? First thing we're going to do, we're going to suggest and estimate that that looks to be about 6 feet. Roughly. Ahem. Now, that being said, this video is timely that apparently in the real world, a rough estimate of 6 feet happens to be 2 meters, referring to some form of social distancing. So we'll say that the diameter of this ball, this sphere, is 2 meters. We're going to work with that. Okay, so the volume of a sphere is equal to, again, 4/3 pi r cubed. Now again, I'm going to tell you the best way of doing this on your calculator is going to be pi times r times r times r times 4 divided by 3. Now, if this thing is totally 2 meters diameter across, that means the radius of this ball is just going to be 1 meter, which is going to make life a whole lot nicer for us. Okay, so the radius of this thing is going to be 1 meter, which means that's the distance from here to here in the ball. So pi 3.14 times 1 times 1 times 1, which is nice because that doesn't really do much, times 4 divided by 3. So essentially, because these are just 1, all 3 of them, I can go 3.14 times 4 and then divide by 3, which will bring up my calculator now. And let's do that. 3.14 times 1 if you really want to. You don't really have to. Times 4, then divide by 3. Lo and behold, this sphere has 4.18 meters cubed. All right, because this is a meter, there's the meters cubed, and from a previous video lesson, or if you can just Google it if you want, that 1 meter cubed has 1,000 liters. And if we've got let's just round to 2 meters cubed, how do you go from 1 to 4.2? Times 4.2. That means we're going to take 1,000 and times that by 4.2, which gives us 4,200 liters, or 4,200 liters. For curiosity's sake, you should look up how many liters per second a human lung seems to consume. All right, this should give you a good basis of how to work out some of these problems from your workbook. Remember, when you have multiple shapes, you're going to be adding them together. So you have to separate them, calculate them separately with a single shape, and then add the total when you have the composite figures together. All right, have a great day.